Okay, Sunday. This is going to be short. I'm just going to do some tasks in electromagnetism, some home assignments. All right. Okay, the first one is we are going to explore a scalar field. So we have this scalar field here, which is just e to the minus y sine x, and it's defined in the region 0 to pi and then 0 to pi m for x and y values. Then we're going to write a Python program to visualize the scalar field both as a heat map, an image, and as a surface. I'm going to try to do this from scratch. It's not it's not the point that I'm going to remember it entirely from scratch, but I can try. Okay, it was of course physics, yeah, and I of course need to go to the test, yes, and then we can just remove. I already have the function, okay. So I already have this implemented. Okay, so here you see x and y. This is the correct function, right? Then it's the same thing again. Rx, Ry is equal to np.meshGrid. That's of course x and y. And let's go with the indexing. Yes, I knew it was something. Okay, and we want a scalar field. So it's a contour plot and a surface, right? Okay. So that contour plot, it's just PLT, would contour this guy, and we have just RX. No, I need the heights, of course. So the height is going to be, let's see. Of course, heights is just h of RX, RY. Yeah. I think I can go with just heights. Either I can go with just heights, or I need RX, RY. Isn't that how you spell heights? No, that's not it. I think it's heights. Yeah, isn't it like that? Yeah. Yeah. Okay. PLT.show. I think we also want CMAP. That should be equal to plasma. But I think this should be all right. Maybe the PLT.axis and equal. And I also want PLT.color bar label equal to just height. Yeah, that should be all right. So P test pi. Okay. I think that's good, but last time I got that guy here. Maybe I have to do Rx and Ry. Let's see. Rx, Ry. Yeah, that is how I want it. Perfect. Very good. Okay. Now, this guy is harder to remember. We can remove this guy away. That three-dimensional plot is hard to remember. It was figure. I can say fig is equal to plt dot figure, right? About fig size. I think he had something like 5, 7, right? And then x, yeah, is plt dot axis. And we want oh, I want it to be three-dimensional. Let's see. What was that argument again? Dimensions? No. Plots. What was that argument? Oh, it's some string, right? Oh, maybe is it that just argument? But there's another argument here. I know it's an argument. Let's just try 3D and just see if something happens. I know it's something like that. We can, that should also be all right. And then it's x dot surface plot or plot surface, and then heights, isn't it? Rx, Ry. And we can go CMAP again. Let's run plasma. Yeah. Oh, let's see. No, Oh, what was that again? Maybe it's surface. Is it surface? It can't be surface. That seems so weird. Surface. No, I don't think so either. No. What was it? Is it three? Is it dimensions? Maybe. That seems silly, but maybe. Oh, I'm going to check. Okay, I had this on. Oh, yeah. It was. Where is it? Projection, is it? An axis, not axis, is access. No wonder I couldn't find the correct value, right? Yeah, there I would have it. Because then I could use the documentation here. Yeah, there's projection. Ah. Okay, now it's either surface plot or plot surface. Projections, what are you talking about? Axis or projection? No? There we go. Okay, so it's plot surface. Plot surface. It always gives me an error for some stupid reason. No, not harpoon. Oh, I haven't fixed this. Okay. No? What is this? With contour, image show. Didn't I comment that one out? Test, plot surface. Maybe it's just heights. Oh. Yeah, that's what I have. Shouldn't that be alright? Let's see. Color bar. Ah, of course. I don't need you. Now it should work. Yes. It seems a bit weird. No, it's correct. I can see it. Yeah. Perfect. Very nice. I remembered it, and that is what I want. There's some small details there, but this is good enough for me. Okay, the gradient of the scale field is a vector field. Right, and calculate this guy analytically. That's pretty easy. We can do this in our brains. This is just partial in the x direction. So that's just this guy cosine x, and then minus this guy sine x, right? No biggie. Write a Python program to calculate and visualize by plotting that analytical result. Yeah, we can do that. Let's see. So we can plot that guy. Def gradient of x comma y. And then the gradient was return. Then it was np dot exponential y. And that's just going to be np dot cosine of x, right? And then I get minus. But it should be a vector, so it should be np dot I could say, or just make it more special, x. No, not x. X component, I could say. Yeah, x component. Component y component is minus np dot exponential minus y and np dot sine. No. np dot sine x, right? And then return should be an array of x component and then y component, just like that. Perfect. And now we want to use that contour plot. I don't need you. This is nice. And we could say plt.quiver rx ry. Then I could use that gradient. So you can say that, yeah, you can just say, that's a little bit stupid. Let's gradient of h. So we could say that gradient is equal to gradient of h. Then we of course just we still give it rx ry. And then here I have to use the x component of the gradient. Then I have to use the y component of the gradient. Yes. That should be correct. Yeah, just a lot of vectors, but it's pretty much correct. And if I just, let's do this so you can see it more clearly. If I remove these two and we do this, you see it, yeah. So you see how the arrows are now perpendicular to the direction of the line. So that is indeed the gradient. Okay, cool. Now write a Python program to calculate and visualize by taking the numerical derivative. Yeah, so you can do the same thing with just the numerical derivative. And that should be pretty easy, right? Numerical derivative, right? We can make an approximation. So if I took limit as x approaches 0 for f of some value plus delta x minus f of x divided by delta x, that is, so f derivative of x is equal to this, but it's also approximately the same thing, just make that delta x pretty small. So we can just use this guy here. Right, and of course you do that with partial, so one of the components will stand still, right? Okay. Def numerical gradient of h. Yeah, stupid name, but it's all right. X and y delta. It will be this. They are. We can just be. We can just use both, but they will be the same, of course. We can say partial x is equal to that function we just wrote, which was just, that's just h of x plus delta x, and then minus h of x. Of course, it has to be x comma y. This is the same as partial x comma y, and divide the whole thing by delta x. Do the same thing here. Y, we don't need this guy here, plus now delta y and divided by delta y. Just like that. Then we can just return partial x. But this should be, again, this should be an array. It's a vector, so it should be partial x and partial y. Yeah, awesome. So if I now substitute this function here for that numerical gradient, we should get the same result. Oh, yeah, I need, that's just, if I call n is equal to 10, and we, no, boom, n, and then we say delta x is equal to, what was it again? Yeah, np, we can just be np dot pi, just to make it clear, or start, stop, I know you don't need 0, but just make clear, and of course y is just the same, the gradient here in delta x, we could of course use the same, but I want to be specific or make things very clear. There you see, so the exact same solution, right? You can see this got a little bit out of hand there, but otherwise it's pretty good. No, it's actually good there, right? Okay, so our solution worked really well. So now let's go to 110, which is the volume integral. So what is the integral of this cube? Right, what is the over a cube for x between a, we have this exponential, you can just write it. Okay, so that it's a triple integral from 0 to a from 0. I can write this as a physicist, which is the volume integral for the function is e to the minus x, and the volume, that's our integral, which is 0 to a, 0 to a, 0 to a. And then we of course have e to the minus x. I do dz first, dy, the x in the end. That's just a, that can go outside, that's just a squared 0 to a e to the minus x dx. That's of course just a squared e to the minus x, so this will get a minus. Right, so this will get a minus, and then we have, of course, e. You moron. E to the minus a and then minus 1, or even better, a squared 1 minus e to the minus a. Just like that. That should be correct. That was, yeah, this guy. Yeah. Okay, what is the integral over a spherical volume centered in the origin with radius a? Yeah, that's just rho. And a, you'll need to do the integral. You could just use your brain. I could have done that earlier, but yeah, it doesn't matter. So the volume is, of course, just 4 pi. So it's a squared divided by 3 and rho 0. Just like that. Should be correct. Yeah. No, divided by 8. Yeah, no. I need, because it should be r cubed. That was it. Okay. My mistake. Okay. Line integrals. A vector field is defined. Make a sketch of the vector field. That's just a vector field that doesn't change. So just E0. There's no, it just goes in one direction. Just like that. And you can see it's uniform in that x direction there. Okay. For r, make a sketch, calculate the line integral, -1 and to 1. Right? So line integral. You can draw it if you want. So if you had this, it went for -1. Let's say this was x and y. So from -1, that will be, let's say -1 was there. So to here, that was the curve C. And our line integral was from -1. You can just write it as you see. That's f dl, which is just from -1 to 1. The x components take care of themselves. E0 go on the outside. And we just have dx like that. From -1 to 1. Yeah. And that's just, you get 1 minus -1, that's 2. So you get 2 E0. Just like that. Yeah. Calculate the line integral from 0 to -2 and 0. That's 0. This is a uniform in the x direction. This is just in the y, so that's 0. Calculate the line integral along a line from -1 to 1. It should be the same. Again, it's just the x component that matters there. So it's the same. And now calculate the line integral from a circular path, but again, it's the same. 1 up to -1, right? And the positive direction, so this is going to be positive then, but it's the same, it's going to be 2e0. So you can do all this complicated stuff, but it's just 2e0, it's the same. Okay. Fluxes of curved surfaces. A cylindrical surface along the z-axis has the radius a and length l. Okay. So it's cylindrical. Right. X. Whoops, that's wrong. X, Y, and then Z. Okay. A cylindrical surface along the z-axis has a radius a and length l. Okay. The surface is oriented with surface normal pointing upward, pointing outward. What is the flux of the field? E is equal to E0 r hat, where r is in the radial unit vector in cylindrical coordinates. Right. Got the flux, right? So here is our figure, and the flux, as we know, the flux is equal to the integral of this surface, so A, and it's f by ds. ds is pretty easy. ds is just one piece here, and the bottom one is just polar coordinates, so that's just r d phi. So we can state that this integral is the same as r d phi, and on the top here it's of course just dz, so that's just dz, just like that. Okay, now since we have that, where are we integrating dz? That's just from 0, or we can do d phi first. That's just from 0 to 2 pi, and dz is just from 0 to l, and instead of r is just a, of course. Right, and ds, what direction that? It's in the r hat direction, so ds is of course a, d phi dz r hat, and f was already in the r hat direction, so now we're in the same components. That's just 1, and the value was e0, so e0 just goes on outside. Okay, then we can just calculate 2 pi. We have e0 2 pi a l. That should be it. Yes. Yes, that's correct. Assume instead, did I show it? Yeah. Yeah. Assume instead that the field depends on the distance r to the z-axis. Yes. What functional form should E of r have for the flux to be independent of the radius a of the surface? Which means that if you think of a two-dimensional field, right? So if I have a two-dimensional field like this, vector field that's two-dimensional, to make the field not matter, of course, if I had some two-dimensional field, that would be something 1 over r, right? So I have to just make my field some kind of 1 over r, and that's it. So if our function is 1 over r, then it should be independent, right? Yes, you can have a constant there if you want, but over r. Okay. A spherical surface centered at the origin has radius a, and a surface normal point outward. What is the flux? Same again, but now it's a spherical surface. You could do the same thing, but what you could do is you can be a little bit clever here. So let's see. We can calculate it, or we can be very clever. Let's see. Okay, the flux is of course this guy. Maybe we just calculate it, it's fun. Okay, the flux is of course that surface. Then you have f, and f is the same thing. So f was just e0 in the radial direction. And we have ds, right? Wasn't that it? Yeah, and then outward. This is not the same because our radial direction now doesn't change, but the radial direction for a sphere, right? It will point just out from the center like this. But the radial direction for a cylinder will always be in the plane, right? So it's not quite the same. But it makes our integral easy. We can either be clever or just write it. Let's just write it. So ds, it's not that hard. So if you have a sphere, right? So if you have a sphere like that, you just need to model that sphere. So a little piece of that sphere is pretty easy. Let's see, so ds in our case as a vector, we still have that bottom one, so it's still r d phi, right? But now we need to compensate for that dz. You do that by r sine theta, and of course the coordinate is in terms of theta, so d theta, and it needs to be in the direction which is r hat. Perfect. Okay, now we can just write it. So we have the same thing again. E0. We have two integrals. Let's see who we're going to do first. It's just r squared sine theta. Then I don't want to do theta first. Let's do d phi first. So r squared sine theta, and then I need d phi d theta. D phi is all around, and this guy is just, like this. Yeah. Okay, perfect. And we have just E0, 2 pi just goes there. So just E0, 2 pi, 0 to pi. And it's not r, so just change it to a squared. And then I have sine theta. Then I have, of course, d theta. And a squared should have been on the outside. Just like that. And then we have done that. You can just integrate this guy. So that's just E0, 2 pi, a squared. We have cosine theta from pi to 0. And of course, cosine, that's minus. We have a minus in front. We can just flip that too. That's also much more fun. So if I just do this, we can just pi and 0. So I can just do 0 pi instead. Then I just get 1, and I get minus minus 1. So this will be 4 pi a squared e0, just like that. Perfect. That's the answer. And then now this one's pretty easy. Assume instead that the field depends on distance. Same thing again. We want it to be independent of the radius. Now this is the same as 1 over r squared. So of course we have to get rid of 1 over r squared. So if E is equal to some constant or 1 over r squared, very good. And there you see. Okay, perfect. That's it for today and this week. And I'll see you tomorrow.